Hi, welcome to Points of Topology extra session. So this will be only 1 hour session, and so this will be only 1 hour session, and the last session will be tomorrow Sunday from 7 to 9, 2 hour session, and yeah, tomorrow session is 2 hour session, and it will be the last session for the whole course. Okay. So if you have any doubt or any question, you can ask me or you can do an email. I shall get back to you as soon as possible. Okay. So remember that tomorrow's session is the last session. So try to try to utilize these sessions in order to clear doubts, concepts, in order to figure out some previous assignments. Okay. Okay. So before starting, let me know am I audible and is the screen visible to you properly? Before starting, let me know whether I'm audible and is the screen visible to you properly. Okay, I hope so. So, okay. Okay. So before starting, let me know, do you have any doubt or any question from previous sessions? Do you have any doubt or any question from previous sessions? Okay. I hope so. I hope there is no doubt from previous session. If you have any doubt or any question, please ask me within the session itself. Okay. So let's So today we shall start with some problems for assignment 7 only. So okay, so yesterday we have solved most of the assignment 7. Now today we shall go through the last problem of the assignment 7. Okay, so let me write the question. Assignment 7, problem 10. Okay, 1 minute. Okay, so the question is the following: a topological space is called Noetherian. A topological space is called Noetherian if for every family Fn of closed subsets of X satisfying Fn plus one subset of Fn for all n. There exists there exists m natural such that if k plus m is equal to Fm for all k belongs to m. Okay, for all k belongs to. So this is by what you know Noetherian topological space. Okay, show that show that every Noetherian space is compact. Okay, show that every Noetherian space is compact. So this question were two things. First is there's a definition by also what does it mean by Noetherian space? So Noetherian space topological space such that for every okay, so leave it. So everybody must have seen something known as Noetherian ring. Sorry. So I guess some of you already know regarding Noetherian ring, right? So it comes under algebra only. So what is a Noetherian ring? Noetherian ring is that if there is an increasing chain of ideas, then after a few steps, that chain becomes that chain stabilizes. Okay. Similarly, there is similar topology. There is concept Noetherian topology, which tells that if we take a collection of what collection of fn's where each fn are closed subsets, okay, such that they are increasing chain, then after certain steps the chain will stabilize eventually. Now question is that to show that Noetherian space is compact, okay, how we can approach. So at least firstly what we need to prove, we need to so okay, directly, 1 minute please. Hmm. Okay, so how we can approach this problem? Is it possible to use directly? Can we consider different? So directly, is it possible to use the definition of compactness? Is it feasible to use the definition to solve this problem? Okay, so for showing some this compact, there is some extra thing also, namely, um, um, so there is the definition and there is something known as finiteness condition. So there is something known as finite intersection property. Finite intersection property. There are two such things, correct? Now, can you think about and let me know? So can you think and let me know how? I mean, or you can use what? You can use method of contradiction. Okay, these things you can also use. So can you please guess or can you please have some approach? Can you please tell me some approach how to solve this problem? Think about it. Let me know. In the meantime, let me find the other problems also. Okay, so let me. So since you are able to response. So let me explain. Okay. So so we are doing this technique. Okay. Method of contradiction. So assume X is not compact. Okay. And let C be an open cover of X having no finite subcover. Okay. Since they're compact, so such a C always exists. Okay. Now choose a C1 from that collection. Okay. Now put D1 is equal to C1. Okay. And similarly define Dn. Now suppose Dn is equal to C1 union C2 dot 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 union Cn. Okay. So now we are choosing Cn plus 1 from C such that Cn plus 1 intersection x minus Dn non-empty. Okay. And define Dn plus 1 is equal to C1 C2 Cn plus 1. Okay. So this is the induction step. Now, so then this implies that x minus d1, this contains x minus d2, contains x minus d3. This is strictly, this is strictly decreasing chain, okay, of closed subsets in X, which contradicts Noetherianness of X. So let me re-explain the argument here. So so okay. So suppose we are assuming that suppose we're assuming X is not compact, okay, and C be an open cover for X and having no finite subgroup, okay, and C1 belongs to C. We're putting D1 equal to C1, Dn is equal to C1 union C2 union Cn plus 1, okay. And Dn is equal to C1 union Cn union Cn, okay. Cn plus 1 belongs to C, such that Cn plus 1 intersection intersection x minus d and non-empty. Now, why such a situation is possible? How that is possible? Can think about it. How possible? How such a situation all is possible? Think about it. Okay, this is first thing. And now we are defining dn plus 1 that is equal to c1 union cn union cn plus 1. Okay. Now x minus d1 contains x minus d2 contains x minus d3 dot dot dot. Okay. Now this is a strictly increasing chain of closed subsets. Okay. This contradicts and this does not and not this is not stabilizing. It's not stabilizing. This chain is not stabilizing. So this contradicts the Noetherianness of X. Okay. So that's why. So I mean, yeah. So that is the argument. So that is the argument. Okay. Now let's go for the next problem. Okay. Before that, let me give them why or not. Okay. 1 minute, please. Okay. Let's go for the next problem. The next problem is that the question is every Lindelof metric space second countable? Is every Lindelof second countable? So first, so hint is that just it is nothing but exploit definitions only. Exploit definitions only. Okay. This problem is really very simple. You need to consider definition and need to think and figure out. Okay. Please take your time, think about it, or I shall explain after a few minutes. Okay. Please take your time and let me know. In the meantime, let me find the next question. You please try and let me know. Okay. So let me explain. Okay. Hmm. So, uh, suppose let x compare. Okay, why I'm saying support x compare? Because this I mean that generally the argument which I'm going to give is somewhat generalized on some other situations. Okay, so that's why I'm first going to the general, right, explain the general situation by assuming the fact that x is compact, and then that similar argument follows without with when we draw the x compact that fact. Okay, so that's why right now I'm assuming x is compact. Okay, so let assume x is compact. Okay, so for every n belongs to n, there exists xn1 xnk belongs to x such that x equal to union of b 1 by n x n I is equal to 1 to kn. Okay, and clearly b is equal to b 1 by n x n I, n belongs to n, n belongs to n, and I belongs to 1 to kn. Okay, and this is nothing but a countable family. This is nothing but a countable family of open set. Okay, and we need to show it forms a base for x, correct? And then we need to show what we need to do. We need to show this forms a base for x. Okay, so now choose x belongs to x and an open set u containing x. Consider r greater than 0 such that b x are subset of u. Okay, now choose a mean n with r by 2 greater than 1 by m. Maximi says that dx comma xmi less than 1 by m. Okay. Now we see that, and we see that x belongs to b 1 by m xmi. This thing belongs sub this thing actually subset of u. And what? And this tells that capital B is a base. Okay, and this implies that x is second countable. Okay, so let me re-explain it. Okay, so let me re-explain. Okay, so the anyway we need to show that any Lindelof space is second, any Lindelof metric is second countable. Okay, and for that, what we're doing, we are first assuming extra fair that x is compact. Okay, so what we're doing is the following. So if for each n belongs to n, there exists x1, x2, xn k belongs to x, such that x belongs to x equal to union of b1 by n xa. Okay, and this tells that capital B, which is b1 by n of b1 by n of x and I, this is countable family open. So we need to show that this forms a base for x. Okay, so for this, what we are choosing some x belongs to a and opens that u containing x. Okay, considering r greater than 0, such that b r x subset of u. Now we are choosing m belongs to n with r by 2 greater than 1 by m. Okay, and x of mi such that dx of x comma I less than 1 by m. Okay, we see that b x belongs to b 1 by m x in a subset of u. This tells that b is a base, and this tells x is second countable. Okay, so yeah, so that is the argument. Now, so this is the assume. So we have initially we have assumed what the extra assumption has been done is that x is complex. So this is the extra assumption, right? So this is extra assumption, extra assumption. Okay, so we need to omit this extra assumption. So for that, now we are going to do. So look, firstly, every Lindelof metric space is second countable. Okay, how? It follows from the fact by a similar argument, by a similar argument as above. Okay, the only change in the argument, the only change is that for each, for every, for all n belongs to n, the only argument we are going to change is that for one minute. For all n belong to n, there exists a countable set xn1, xn2, xn3, and then the countable balls b I n belongs to n, I belongs to n, would form a base for x. Okay. So yeah. So what is the only need you need to change is that in the above argument. So instead of finite, we need to use what? We need to countable collection. Okay. Countable collection of x1 is to xn's and a countable open balls such that that form a base of x. Okay. So that's what it is. Okay. Now, okay. Now, okay, there is one interesting question I must admit. This is out of the assignment, but I must explain this or explain this thing. Show that circle, that is x square y square 1, and ellipse x square plus a square y square b square equal to 1. These two things are homeomorphic, but circle is not. But circle is not homeomorphic with. But circle is not homeomorphic with um, uh, hyperbola. X square by a square minus y square by b square equal to 1. Okay. So basically, so this is circle. Okay. This is ellipse. Okay. And somehow this is a hyperbola. So this is x-axis, y-axis, this is also x-axis, y-axis. This is x-axis, y-axis. Okay. This is x square y square equal to 1. This is x square by a square plus y square by b square equal to 1. And this one x square by a square minus y square by b square equal to 1. Okay. So this is a, this is b, here this one a, this one is b. Okay. So what I need to show that these two are homeo, circle and ellipse are homeomorphic. But but uh but the circle and hyperbola is not homeomorphic. Okay. So how we can approach? So what we need to show is that there is a continuous one. So we need to show, and so for this part, so what we need to do for, we need to show existence of bicontinuous function in between. And for other part, that is for circle and hyperbola, we need to show such a function cannot exist. Okay. So now think about it and take your time. Let me know how to approach this problem. In the meantime, let me find out the other problems. Okay. Hmm. Okay. Okay. So let me explain this. Okay. So first of all, as you might guess, the circle is a homomorphic. Why? Because if we stretch the circle along the axis, then it will somehow turn this. But circle and hyperbola are not homeomorphic because if you stretch, you cannot get um, hyperbola from circle. That is my point. Okay. So okay. So we are denoting the circle to be C, okay, and ellipse to be E, hyperbola to be H, okay. So we are defining a map little f, okay, from where to where? From circle to ellipse, okay. How we are getting x comma y goes to x comma y, okay, and the reverse map G, how we are defining x comma y goes to x by a comma y by b, okay. Clearly, these two clearly f and g are continuous. Okay, and f composite g is equal to g composite f is equal to identity map. Okay, so this tells that circle and ellipse are homeomorphic. Okay, is it clear? So in order to show circle and ellipse homeomorphic, what we have done extra? We have not done anything extra. One. So circle and ellipse are not homeomorphic. Okay. So 1 minute, please. Hmm. But so this tells what? This tells that if we consider stretching function from circle to ellipse, that is just this one is the stretching. Sorry, so this one is one stretching, this one is reverse stretching, and there's a continuous that their corresponding composition identity. Okay, this tells that C and E are homeomorphic. Okay, so yeah, so that's all. So now, So these are homeomorphic. Okay. So this tells that circle is homeomorphic. Now we are going to show the same does not hold true for circle and hyperbola. Okay. So so the okay. So so that is we need to show there does not exist any kind of bicontinuous bijective function. So directly we cannot but directly we cannot show that. So for that, what we need to use a connected complex circle. Look, the circle is fully connected. Okay, but if they're homeomorphic, so I mean, look, since continuous image of connected space is connected, since continuous image of connected set is connected, this implies hyperbola must be connected. Why? Since circle being connected. So since continuous image connectors were connected and since circle is connected, so hyperbola is also connected. Okay. So this tells that hyperbola and circle are not homeomorphic. Okay. So yeah, so this is it. Now, okay. So now the next question is the following. Okay, so now let me go for the next question. The next question is that 1 minute, please. The next question is that if in R2 the set of all straight lines is taken as subbasis, then the topology generated by it is the discrete topology. If in R2 the set of all straight line is taken as subbase and topology generated by it is a discrete topology, okay? So yeah, so is it true or false? True or false? So okay, think about it and let me know. So basically what we're doing, we are considering the straight lines or subways, okay? And we have to consider topology, the discrete topology not. So in order to check something with discrete topology, what I need to do? So the hint we need to check whether singletons are open or not. Okay. Hint is that hint whether singletons open or not. Okay. So whether single is open or not. So this is the so these are the things. So you need to consider. Okay. So think about it. Take your time. Let me know. So look, so what we need to observe, we need to observe whether singletons are open or not. Okay. So any singleton point is nothing but intersection of lines, correct? Any point in R2 is intersection of two lines, right? So this tells that any point is open under the above mentioned topology. Okay. So this implies it is what? It is discrete topology. Okay. So this is the argument. So is it clear? So basically, what we have checked? We have checked whether any singletons are. Oh, sorry. What we have checked? We have checked that whether any singletons are open or not. Okay. Any singleton open. That is what we have checked. Okay. So now any single point is nothing but the intersection of two lines. So that tells any point is open under the above mentioned topology. So this tells that it's a discrete topology. Okay. Now, question 2. Okay. Now, next question is that if beta 1 is a basis for a topology tau 1 on a set X, beta 2 is a basis for a topology tau 2 on X, and if tau 1 subset of tau 2, this implies beta 1 subset of beta 2. So is it true or false? So there are two topology with basis beta and beta 2, and the tau 2 is finer than tau 1. Then what you can guess that is the beta 1, the beta 2 is bigger than beta 1. So firstly, in order to understand this, you need to realize what does it mean by tau 2 is finer than tau 1. This means what? This means that in tau 2 there are more number of open sets than tau 1. So this means what the neighborhoods, that is the basis elements of tau 2 is quite much finer than tau 1. So this tells that beta 1 beta 2 subset of beta 1. Okay. Now let me mathematically do it. Okay. So let x belongs to beta 2. Okay. Sorry. So take u belongs to beta 2 and x belongs to u. Okay. This implies what? This implies, okay, so answer really false. Okay. And counter example. কিভাবে, sorry, the counter, what should be counter example? Take x equal to triple tensor A, B, C, okay, with the discrete topology. Here they give the discrete topology. And we're considering beta 1, A, B, C, A, B, okay. And considering beta 2 to be A, B, C, B, C. So these are both base of discrete topology on X. Okay. But if you observe that the tau 1 is equal to tau 2, okay, so this stays it. But the beta 1 is not subset of beta 2, okay. So there is a contradiction. Anyway, the point is that since the open sets of tau 2 are finer than tau 1, so the open sets, the base elements of beta 2 is contained inside beta 1, okay. So that is the most natural case for the situation. Okay. So um, okay. So there is one last question I must mention is that if beta is equal to all squares centered at origin in R2. Then the topology on R2 jet. Then the topology on R2. Sorry. The topology on R2 having beta as a basis is the usual topology. Okay. So basically what we've done, we choose the all squares to be centered at origin, and we are now saying that usual topology not to, I mean, so we are now saying that is the topology generated by beta. That is if the topology generated by beta is the usual topology of R2 or not. Okay. So for that, what you need to check that this type of open sets are open in the topology generated by beta or not. That is what you need to check. Correct. So think about it and let me know the next session. I am not going to solve this because this is very easy. You need to check only the whether the original basis element is the usual topology is also base element on the topology and beta on. This is what you need to check, and that is very easy. Okay. So yeah, so that's all for today. We shall meet on the next. We shall meet tomorrow, Sunday, from 7 a.m. to 9 a.m. That will be the last session. So if you need out any question, please ask me in the session, or also you can do an email. Okay. Thank you. I'm in the session.